Okay, so let's get started, and we're going to start working through this lab 2. Now I'm going to do all these parts in one long video, and I'll put timestamps in the description or a comment or something just so you know where everything is and you can skip to what you need. So for the first part of your lab report, it wants you to make a data table for all of those %t values, which I have here, that you measured at different wavelengths. And then it wants you to calculate absorbance for it, show that in a data table, and then plot them in a graph. So we're going to do all of that, and I'll show you how to do it in Excel too, just to make it easy for you. So for the first part, we're going to be converting these %t values to A. So as you probably noticed, I have a separate column here for T. I do this because I believe in the numbers you sent me, I think you used %t and not t to calculate absorbance. If you recall, the formula to calculate absorbance is negative log of t, not %t. So if you don't convert your %t to t, then your absorbance value is going to be wrong. In fact, it's going to be negative. And if your absorbance value is negative, that is never a good thing. It should always be 0 or positive. Always remember that. You should never have a negative absorbance, or else something is probably wrong. So let's go ahead and do that. So first I'm going to convert %t to t in this column. So I'm going to put equals in this cell here. That's just telling Excel that I'm going to do a calculation or I'm going to do some kind of formula. In this case, we're just going to take the value in this cell in column B here. So B2 is going to pop up. We're going to divide by 100. And that converts to a decimal, right? So now that's converted to a decimal and it's t, now we can plug it into that formula that we were just using and calculate absorbance, right? So let's do that. We're going to put in equals negative log, and that'll come up as a formula in Excel. That's what all these are, as a function here. So we can double click this and then it'll show us what we need to do. It needs a number to put in the log formula, and we have a number. We want t. So we're going to click this, gives us our number, and it also wants a base. We're doing base 10, which is always what you're going to do for this. You do not need to know that, but just know we can leave that blank, so I'm not going to put a base in. Excel will assume that that's 10, so we'll be fine. And there's our absorbance. So now we've got absorbance. I have it rounded to the third decimal place. You may want to change it for sig figs or whatever whenever you do this on your own. So now we have absorbance for 400, and we can do the same thing for all of the rest of the wavelengths, but we're going to be lazy, and we're going to highlight these two cells, these formulas in them, and then double click this little lower right hand corner of the box, and it fills it in for us. So now we have all our absorbances, and you're probably wondering, hey, these bottom two are negative. What the heck is up with that? You just said that they have to be 0 or positive. So what's going on here? Well, what's going on is that your %t values for wavelengths at 590 and 600 are above 100%, which is impossible, right? Because the way a spectrometer works, what you use to get these %t's is it shines a beam of light through your sample, and then it has a detector on the other side to see how much of that light is recovered after it passes through your sample. So the less light recovered, the lower your %t, the higher your absorbance, right? If you have something that's entirely clear, like water, and no light is absorbed, then your %t is 100. All of the light passes through and all of it's detected. If it's above 100, that means you're detecting more light than you put in, which is impossible unless you have some outside source. So what this means is that you probably had some experimental error where some outside light got in and reached that detector, leading to this higher than 100% T. So that's why your absorbance values are negative, because this is impossible to have, so is this. And that's reflected in the math here. You don't need to worry about it. I don't think you'll be counted off for having this in your lab report, but just know that theoretically these should be 0 and these should be 100. So just understand that. absorbance should be 0 or positive. It shouldn't be negative. All right, so now we're going to go ahead and make our chart. I'm going to bring this to the big screen here just so we can see what we're doing better. So I'm going to get a scatter plot. I'm over here in Insert, in the Insert tab, and I'm going to come down and pick Scatter Plot here. Now it's trying to go ahead and autofill a plot for us, but I don't want that. So I am going to go to, I right-clicked the chart here, and then went down to Select Data. And I'm just going to delete all of this. I'm just clicking these and hitting Remove, because that is not what I want my chart to be. Hopefully you just get a blank chart when you do this. For some reason it tried to autofill the data for me, but it never does it right. So, oh my gosh, I'm an idiot. Okay, let me go back in and do this. I didn't hit OK. I hit cancel. Okay. So alright, so you should have a blank chart like this. What we're going to do is we're going to right click and select data, and we're going to go to this legend entries box here, click add. Alright, so now it wants to know what values we want to put in our x-axis and our y-axis. So let's start with the x-axis. In our x-axis, we're always going to have our independent variable, or what we know, right? So it's not going to be something that we're measuring, it's going to be something that we control during the experiment. In this case, what we controlled was our wavelength, right? You input the wavelength into the spectrometer and then just measured %T from that. So this is going to be our x-axis. So I put my cursor in this box, highlight all of these, and there we go. So that's all set. As you can see, our all of those cells are now included in here, in this mess of letters and dollar signs. So now in the y value box here, we're going to delete this 1, and we want what we measure in here, our dependent variable, right? What we measured in this experiment, in this part of the experiment, was %T. Now, what we really are looking at is absorbance. That was the point of calculating it. So that's what we're going to put on our y value. This plot is going to be wavelength versus absorbance. All right. Okay, okay. And there's our graph. I'm going to make this a little bigger, and I'm going to pretty it up. I'm just going to, you do not have to do everything I'm doing here. I'll point out the important stuff to do. I'm going to get rid of the legend too. We don't need that. We only have one data set of data here. So, okay. So I'm also going to format this axis. I'm doing this because I don't want all this empty space here on either side. So I'm going to change the bounds to 400 as your minimum, because that's the minimum wavelength that you used, and then your maximum as 600, so that's the maximum wavelength you used. Here we go. You do not have to do that. I just did that because I think it looks better. It's not as messy. I'm also going to right-click this and say Format Data Series. Make sure it says Data Series and not Data Point. And then this screen will come up, go to the Paint bucket, and say Solid Line. There we go. Make sure you do that. That's good to have in this kind of graph. And the next thing is we need our axis titles and our graph title up here. So chart title, axis titles, and we should be good without anything else right now. So let's change this chart title to something like absorbance versus wavelength. And I'm going to put for solution D. That was the solution you used for this part of the experiment. So next we need our axis titles. So this is the x-axis, which is where we have wavelength. And always, always, always remember your units. We have wavelength in nanometers. So I'm going to include that in this title. And then our y-axis is absorbance, which does not have any units, so we can just leave that as absorbance. Alright, so you already know your lambda max because you used it to do the next part of the experiment where you measure the absorbance of the unknowns using lambda max, which was the wavelength at which the absorbance was the maximum that it could be out of all of these data points. So we can better visualize that lambda max here as the peak of this curve, right, which is right here. And that is over 460 nanometers, which is what you found lambda max to be. So that all checks out. So I'm going to click on this data point here. I'm clicking on the data series right now. You can see all these points are selected. I'm going to click again. This is just the single point. You can see it's only selected now. Now that it's only selected, I'm going to right click, format data point, and oh no, not format, sorry, add data label. We're just going to click that. Little box will come up here and drag it up a little bit. You can see a line connecting to it. So you need to label this point as lambda max. So let's clear that box out, and we're going to go to insert, and we're going to insert a lambda symbol. So I have it right here. It's right here in the chart here. You may have to dig around for it a little bit, but it's in here towards the upper part. And I'm going to click this and insert it. So it's here now. It's kind of hiding behind my cursor there. And I'm going to type max next to it and equals 460 nanometers, because that's what we found it to be. There we go. So now it's labeled. We know where lambda max is on our graph. We've clearly pointed it out. Our axes have titles now. We have a line through all of the points, a graph title. We should be all set. So here's our graph. So let's move on to the next part. This is all the fun calculations that we got to do. So I'm going to drag this Excel chart over here, and we're going to go down to the calculation portion, or up rather, and we can go through this step by step. Alright, so these are the 4 solutions that you had, and this is the components that made up each solution that I've put up here in this table. I've also included the concentration of your iron 3+ solution and your thiocyanate solutions. They were both the same concentration in their respective solutions, so I just put they equal each other. This is all your initial concentration of that. I also put the formula for Beer's law, which we're going to be using later, and I'll get into how once we get there. So to start, it wants you to find the number of initial moles of iron and thiocyanate that you used. So to start with, we're going to start with solution A. So to start, you had 10 milliliters of the iron solution and 1 ml of the thiocyanate solution. So we can, thankfully, in order to calculate moles of initial moles that you added of a solution, you'd need concentration and volume, right? Well, we have both of those. We have concentration, the initial concentration of both of those solutions, and the volumes. So molarity, the concentration up here, is moles per liter, moles divided by liters. So if we multiply by the volume that we added in liters, we're left with moles that we added in that aliquot of solution. So I made this chart down here, which is just detailing all of these calculations that we're going to work through. Shoot. Sorry, my mic went out, I think. Okay, is this still working? Okay. All right. So now, okay, we're going to do this calculation of initial moles. So I'm going to go into Excel and type equals, which again is just telling it I'm going to calculate something or that I'm going to put in a formula. So we're going to do equals, and then we're going to do the concentration up here, which is 2, I'm going to do parentheses, 2 times 10 to the -3rd, okay? And multiply that by our volume, which is up here. I'm going to type a parenthesis though, because this volume is in milliliters, right? We need to convert that to liters. So we're going to do that, divided by 1,000, and enter, and there are our moles, initial moles of iron. Now what's cool is we can, just like we did in the first part, we can just drag this box over and it will do this same calculation for thiocyanate. Since the concentration doesn't change, we don't need to worry about the concentration changing up here. It's just going to be this concentration multiplied by this volume divided by 1,000. So I can just drag this over, and there you go. Now if you notice, I have these set to scientific notation. If you go to the top of Excel up here, in the Home tab, you can see in the number section here, there's this little drop-down bar, and you can click scientific down here. the general would be way too big. Like so I like scientific for these very small numbers because it's just easier to see it in the cell. All right, so we have those. Now we need to find the molar concentration of iron thiocyanate. So it says use Beer's law and assume that EB at your lambda max has a value of this number or this number, depending on if you have a round cuvette or a square one. Now you told me that you had a square cuvette, so that means we're going to use this constant in our Beer's law formula. So I'm going to open my MS Paint here. Let's break down Beer's law real fast. So in Beer's law, we have A equals epsilon B C. Now these two variables, epsilon and B, they're just constants that we don't really need to worry about right now. This is molar absorptivity, changes depending on what substance you're using, and B is the length of essentially the cuvette that you're using, or whatever test tube. But in this case, they're giving this to us, and usually it will be given to you. So this, for us, you used a square cuvette, so this constant is going to equal 5,375 liters per mole. So we can write that out, 5,375 liters per mole. Put that in parentheses, times C. And remember, C is concentration, and that's going to be molarity, or moles per liter. That's important to point out because, as you'll see, this is all equal to A, right? Remember, when we were doing the absorbance versus wavelength, that I said absorbance doesn't have any units. This is why, right? Excuse me, this constant has units of liters per mole. Concentration is moles per liter. If these multiply together, those cancel out and leave us with just absorbance with no units. So how are we going to use this to calculate the concentration of our iron thiocyanate? Well, what we're going to do is Beer's law states that there is a relationship between concentration and absorption of the solution. We have absorption of the solution. That was what you calculated up here. We still need to do that. I forgot to do that up here. So just like we did on the last page, we're going to convert %T to T. Do that. Divided by 100. Converts that to T. And then absorption. We're going to do negative log. Double click that. Of T. And there's your absorption. So we have absorption here. And we can substitute that in for A, and then divide A by 5,375 liters per mole. That'll cancel these out, and once we do this division, we'll be left with concentration. And since these units are being divided on this side, the liters per mole, it's a horrible L, they're going to switch, right? The numerator becomes a denominator and the denominator becomes a numerator, becoming moles per liter concentration, the units that we want. So that all checks out. So let's actually do that math now. So what we want to do is, as we showed in my horrible MS Paint drawing, is we want to divide the absorbance by that constant here they gave us, 5,373 or 75. So we're going to type equals. I'm going to go up here and click absorbance and divide it by 5,375. And there is our concentration in molarity. I should add that to this here. There you go. So in moles per liter is molarity. So there's our concentration of our product. So now we need to know the number of moles. Well, that's pretty much the same as our calculation over here, right? Is where we just multiplied the concentration by the volume that we added. So we're not adding this. This is what we made. But we do know how much is present based on our total milliliters of solution. This is why I added this column up here, is we knew this was given to us from this document here and what you did in the lab. And I just added up all of these volumes to the right here, and all of them came out to 15 milliliters of solution. So we're going to use that to calculate the moles of product in solution A. So we're going to type equals, and remember we just need to multiply the concentration. We're going to multiply that by the volume in liters. So we have this in milliliters, so we need to convert to liters by dividing by 1,000. And there's our number of moles. So that's our number of moles of product that we form. So now it wants us to find the moles of reactants, our moles of iron and our moles of thiocyanate. So this calculation is a little tricky. So you need to think about what is actually happening in this reaction. If we go up to the top of this document, we can see the reaction written out for us. 1 mole of iron reacts with 1 mole of thiocyanate to make our orange product here, the iron thiocyanate. Now, this reaction occurs in a 1-to-1 ratio, right? All the product, or all the reactants, 1 mole of each combines to make 1 mole of product. Pretty straightforward. So knowing that, if we know how much product, how many moles of product we end up with, we're going to know how many were consumed to make it, right? So if we take our initial, which is much larger than what we actually ended up with for both of our reactants here, if we subtract this number, which is the amount that we knew had to be consumed from each of these starting reagents, we can calculate the amount left over, the final number of moles. So if you think about it this way, I like to think of this as putting a blue ball and a yellow ball side by side and smushing them together, and it makes a green ball, right? And then if you came into the room and saw that I had 4 green balls sitting on a table, then you would have known that I had, in order to make that, I had to have 4 blue balls and 4 yellow balls, and then combined all of them together to make this. Now we had excess of these reactants, right? We had more than enough to make product, and we only made this much product here. So we can just subtract each of these initial molar amounts here by the final moles of this product, and then we'll know how many are left over at equilibrium, the end state of this reaction. So let's go ahead and do that. Let's do iron first. So we're going to take the moles here, the initial, and subtract them by the moles of the final product that we made. And there you have it. That's our moles of iron and the final moles of iron. We're going to do the same exact thing here. Now I'm not going to just drag this because that wouldn't give us the right calculation here. I'm just going to do this separately. We're going to do initial here minus your final here. 11, enter, and there you go. So they're different by about a factor of 10 here, but they are different. Now the last step is we need to calculate, there it is. We have our moles. Now we're going to calculate our final concentrations of these reactants at equilibrium. So how are we going to do that? Well, we know our moles of each of these reactants in the final part of the reaction, the final moles of each of these. And just like we did when calculating just like we did when calculating moles of product here, we know our final volume too. We have 15 milliliters at the end. So molarity is moles per liter. We have moles, and we know the volume in milliliters. Convert that to liters, divide the moles by the liters. We've got concentration. Just a simple division problem. So we're going to start with the moles here. And we're going to divide by, put a parentheses in here so I can divide it. Divide this final solution amount by 1,000. And there's our final concentration of iron. We're going to do the same thing over here for thiocyanate, equals, we're going to do our final moles for that, divide it by, put a parentheses in, same volume because they're in the same solution here, divide it by 1,000 to convert to liters, enter, we've got our concentrations. So now the last step, KF, the worst one of all, right? Well, like most reaction constants, it follows a straightforward pattern where you calculate it by dividing the concentration of the product at equilibrium by the concentrations of your reactants at equilibrium. Well, we have that. We have our final concentrations for both our reagents, and we already calculated our concentration for the products over here, for the product, excuse me, and they're all molarity, so it's just a simple fraction that we got to solve. So let's set it up. We're going to put equals in. We need our product concentration, which is our iron thiocyanate here, and it's going to be divided by the product of both. Well, that sounds contradictory when we're in chemistry. I meant that mathematical product of our reactants being multiplied together, the concentration. So we're going to divide it by the multiplication product of these two concentrations. So our iron and our thiocyanate here. So those are multiplied together. They're closed parentheses, so that all works. We hit enter. There's our KF. It should be a mostly whole number. It won't be any like scientific notation, something crazy for this experiment. Now it can be in different experiments, depending on what you're dealing with. But in this case, it is above 0, and it's not a very small decimal like all of these values. So, as you've probably been curious about, the last step mentions that when you calculate KF, remember to report this value with the proper units. So reaction constants are always going to have weird units. And I think the best way to work through them is to literally draw it out. So what we're going to do is I'm going to make a new sheet here. Save that. So let's just write out KF, but we're just going to write it out in terms of units. So going back up here, we'll look at the formula. Here's our formula for KF. I'm just going to write it in terms of units. So on the top, let's draw our fraction here. On the top, all three of these concentrations are in molarity, moles per liter. I'm just going to write out moles per liter here. Keep that simple. I don't know why I drew a capital L there, but oh well. All right, so moles, and on the denominator, we have two reactants that are each moles per liter, and they're being multiplied by each other. So we have moles per liter up here in the product, and then two reactants that are each moles per liter. So we're going to say equals, and let's go ahead and do this multiplication out. So the numerator is going to stay the same, and on the bottom we'll have moles squared and liters squared. So now we're just left with a fraction in the numerator being divided by another fraction in the denominator. Well, if you recall back to old school math, you can solve this by, if you're dividing a fraction by another fraction, by multiplying the numerator by the reciprocal of the denominator. So I'm going to take this down. Here's our numerator, just moles per liter. And we're going to multiply it. Can't draw an X anymore. Okay. By the reciprocal of the denominator. So we're going to multiply it by L squared over moles squared. Excuse me. So now we're just left to cancel units out, which is all we have. So on the numerator here, excuse me, on the left side here in the numerator, we have moles, and on the right side in the denominator we have moles squared. So we can cancel out one of these moles on the bottom. Cancel out this. We're just left with moles down here in the bottom. On the other side, we have, on the denominator side of the left fraction, we have liters, and then we have on the right side liters squared in the numerator. So just like the moles, one of these is going to cancel out, and these liters are going to cancel out. which leaves us with just liters per mole. So another way you can think about this is liters per mole is the same thing as, not the same thing, but it's the opposite, the inversion of molarity, right? Normally molarity is moles per liter. This is liters per mole. So another way you can write this is you can write molarity to the -1, which is pretty much the same thing as saying 1 divided by the molarity. I wrote that out because sometimes they'll give you this unit instead of these. If you're writing out a problem or having to write in units, I would stick with this because there's no confusion as to what you're meaning. Sometimes you may get confused with what you're writing here, or like what you need to write. If you like doing it this way, go ahead and do it. I always do this because that's the one I see when I do these calculations and, cross everything out. And it's just that way I know there's no confusion. I know exactly what I'm putting down. So now that we have that, I'm going to go back to this. Sorry, go back to this, and I'll put parentheses liters per mole. That's our units. So I think that covers everything. Now you can just go back through and do the same thing for all the other steps. Make sure you go through and understand why you're doing the math. That's always the hardest part for chemistry, is understanding not the math, not what math you have to do, but why you're doing that math. So if you have any other questions, just let me know. I know you had some questions about statistics like Q-test and confidence limit. So if you need me to go through those, I can. But yeah, other than that, just let me know if you got any questions, and I'll see you later.